So, good afternoon, everyone. So, let's start our last talk in this SABS this year. So, our last speaker is Luis Apolo from BIMSA. He will talk about logarithmic corrections to black hole entropy and the asymptotics of weak Jacobi forms. Let's welcome.
Okay, so let me begin by thanking the organizers for the opportunity to speak here. This has been a great congress and I have enjoyed it very much. So today I will tell you about log corrections to black hole entropy and how you extract these log corrections from the asymptotics of weak Jacobi forms. So let me begin by giving some motivation for this work. And the motivation comes from ADS-CFT. So in ADS-CFT, a semi-classical description of quantum gravity in ADS-3 imposes several holographic conditions on the dual CFT2. So these conditions include the existence of a large n limit, which for a CFT2 means a large central charge, which goes inversely proportional to Newton's constant, large n factorization of the light states, and a sparse spectrum of light states, which means that the spectrum does not grow with n. And about 10 years ago, Hartman, Keller, and Stoika made this concept of sparseness precise. And they found that this sparseness condition is given by this expression here. So the density of light states is bounded by this Hagedorn type of growth. And this expression is valid for the light states, so for energies in this regime. Here, 0 corresponds to the black hole threshold, and minus C/12 is the energy of the ground state. And what they found is that if you impose these conditions of sparseness, large n or large C in this case, and motor invariance, you find that the free energy of the CFT is universal. So the torus partition function of the CFT2 written here matches the partition function that you would compute in the semi-classical approximation in three-dimensional gravity. So in more detail, the universal free energy of a CFT2 takes this form. So this is the expression when you are at low temperatures. So beta here is an inverse temperature. This expression is the same that you obtain from the vacuum. So there's a vacuum dominance in this regime. And at high temperatures, you obtain the motor image of this expression here. And from the gravity point of view, this is what you obtain from a BTC black hole. Because of this, sparseness, motor invariance, and large n also imply a universal density of states. So for light states, by assumption, we take them to be sparse in this sense. But for heavy states, the growth of these states, the density of these states is given by Cardy's formula. So from the point of view of gravity, this is compatible with the fact that the entropy of black holes grows in this way, whereas this density of light states is also compatible with the number of perturbative states that you expect in a theory of supergravity. So this analysis by Hartman and Keller and Stoika is not sensitive to the light spectrum of the CFT, so it works universally for all holographic CFTs. In addition, it extends the regime of validity of Cardy's formula. So Cardy's formula was originally derived in a regime where the energy is much greater than the central charge. But thanks to HKS, we can extend Cardy's formula to this regime, where this symbol here for us means that the energy scales linearly with the central charge, and the central charge is taken to be much greater than 1. So in particular, this justifies the derivation of the Bekenstein-Hawking entropy for BTC black holes in the semi-classical regime, where we take the central charge to be much greater than 1. Now, many BPS black holes in supergravity feature an ADS2 near horizon geometry that can be uplifted to ADS3. And so this leads us to the following question. What do the holographic conditions that I mentioned before, namely large n and sparseness, have to say about the entropy of such BPS black holes? So what I will do in this talk is I will extract the asymptotic density of states in what I will call a holographic weak Jacobi form. I will explain what I mean for a holographic weak Jacobi form soon. And these holographic weak Jacobi forms can be interpreted as a gravitational path integral. And I will focus on the logarithmic corrections to Cardy's formula and identify two regimes in these weak Jacobi forms. So here's Cardy's formula. Here are the logarithmic corrections. So I'm interested in extracting these coefficients. So we will find that weak Jacobi forms have a universal and a non-universal regime. In the universal regime, these coefficients here are independent of the density of light states of your CFT, or rather the density of light states of your weak Jacobi form. And in this regime, we will be able to extend the validity of Cardy's formula beyond what HKS did. So HKS performed their analysis for a partition function. We're dealing here with a weak Jacobi form, which is a holomorphic object. So that's the reason why we're able to extend this a bit. And we will see that this universal regime of a weak Jacobi form captures the log corrections of certain BPS black holes in 4 dimensions, okay? But in addition to this, we will find that weak Jacobi forms also feature a non-universal regime. And this is a regime where the log corrections, so these coefficients here, are sensitive to the density of light states. So these corrections will be dependent on the spectrum of your theory. And we will see that this has an application for 4-dimensional and 5-dimensional black holes in supergravity, where indeed the log corrections turn out to lie in this non-universal regime. Okay? Asymptotically flat black holes, yes. I'll get it from supergravity. But in principle, like this weak Jacobi form will be, for example, the elliptic genus of the CFT dual to the ADS3 theory. Yeah, but in principle, for this calculation, I only need the light state data. So I don't need to know what this object is. I just need the light state data. In any case, for a weak Jacobi form, if I give you the light state data, you've determined the object completely.
So how is this precisely different from us?
Well, here basically we're using holography. So Sen did this, he looked at this ADS2 near horizon geometry, and then he computes the contribution of basically the massless spectrum there. So I'll explain a bit later on. We will do an uplift of what Ashok did to go to ADS3. And then the object that we consider is some weak Jacobi form. Okay, so I will show it a bit later, but this will be like in the second half of the talk. Okay, so this is the motivation. This is the plan of the talk. What I will do now is tell you a little bit about weak Jacobi forms and what I mean by a holographic weak Jacobi form. Then I will tell you how I extract the asymptotics of these weak Jacobi forms, and then tell you about matching to the log corrections of different black holes. So also to address your question, these corrections have been computed before. So it's not like we're computing something new, but we're showing how we can extract these quantities from a different perspective, okay? Okay, so let me say a few things about weak Jacobi forms. So these are holomorphic functions. They are characterized by a weight and an index. For this talk, I'm going to assume the weight is 0 for simplicity, even though for one of the applications, the weight is not actually 0. Okay, and I'll say, yeah, okay. And these weak Jacobi forms have the following features. So they transform nicely under modular transformations. They also transform in this way under elliptic or spectral flow transformations. And these properties of weak Jacobi form imply that they admit a Fourier expansion. So by this, I mean an expansion of this form. Here, C are the degeneracy or the number of states for a given N and a given L. Here, N, we can think of N as an energy. We can think L as a charge. And our goal will be to extract these numbers when N and L are large in a sense that I will make precise soon. And an important thing about this Fourier expansion here is that this sum goes only for n greater or equal than 0. Now, these two transformation properties of weak Jacobi forms imply that the Fourier coefficients depend on something that's called the discriminant, which is this combination of charges and the index, and L modulo 2 times the index. And they satisfy the following property: these coefficients are 0 if the discriminant is less than some minimum value, delta naught. So this is the minimum value of the discriminant. So the spectrum of weak Jacobi forms looks something like this. There are some states with a negative discriminant delta here. There's a minimum value of the discriminant, which is like the ground state. These are known as polar states. If we want to eventually give this object a gravitational interpretation, which we can do in the cases I will discuss today, this would correspond to light perturbative states from the point of view of gravity. And we also have heavy states with a positive discriminant, which again, from the point of view of gravity, would correspond to heavy black hole states. Okay, so one reason to look at weak Jacobi forms is that they are simpler than partition functions, but have a richer structure than a chiral partition function. For these weak Jacobi forms, the polar states fully determine what the weak Jacobi form is, meaning that they fully determine the nonpolar terms. And it is well known that weak Jacobi forms are relevant in string theory and the ADS3 CFT2 correspondence. So an example worth keeping in mind is the elliptic genus of an n equals 4 CFT2, which is a weak Jacobi form of weight 0 and whose discriminant is proportional to whose minimum discriminant is proportional to the central charge. Okay, but in this talk, we're not interested in just any kind of weak Jacobi form. We're interested in what I will call holographic weak Jacobi forms, which meet some additional conditions. So the absolute value of the minimum discriminant is much greater than 1. So this plays the role of our large n parameter. And we will assume that the spectrum of polar states is sparse. Okay? And so these are conditions that make this object compatible with a semi-classical gravitational description. Okay, so what's a sparse weak Jacobi form? A sparse weak Jacobi form is one whose polar states satisfy the HKS bound and lead to a universal growth of non-polar states. So this is something that was studied before by Benjamin and friends. So for a weak Jacobi form, this HKS bound on the light states takes this form. And if you impose this condition, then you find that the density of states with a large discriminant, the density of heavy states, take this exponential form, which is what Cardy's formula looks like for a weak Jacobi form. And this expression, again, is valid in this regime where delta scales linearly with delta naught. And we have to keep in mind these regimes because they will be important for the rest of the talk. But it turns out, so this work had been done before, that for us it's not enough to have this sparseness condition. We need to distinguish between different kinds of sparseness, meaning we need to distinguish between different kinds of growth of these light states. So we will distinguish between fast growth, which means that the density of light states satisfies this condition, this bound, which looks like the Hagedorn growth, except for this parameter gamma here, that it's allowed to be greater than 0. And we will see that for this fast growth, the density of nonpolar states of the weak Jacobi form is universal in this regime. But we will also consider slow growing weak Jacobi forms. And these are forms that have a sub-Hagedorn growth. Now, since this function here, so they're bounded by an exponential of this function depends on 2 parameters. So basically the energy and the charge above the ground state. And so we characterize the growth of this function by scaling the arguments here by some parameter lambda much greater than 1, so that this function scales in this way, okay? An easy example of this is the case where we forget about the charges. We just focus on the energies on n. So in this case, the density of light states would be bounded by something that goes like delta minus delta naught to power alpha. And this power alpha is less than 1. Okay? So this is exactly the type of behavior that you find in theories of supergravity. Okay? And what we will see is that for these slow growing forms, there's both universal and non-universal behavior for the coefficients for the density of heavy states. And this behavior will depend on how the different parameters of the weak Jacobi form are related to each other. Okay? I will make this more precise soon. Say that again? Yeah. Yes, yes. Well, yeah, generic is fast growth, and it's actually not easy to find examples with slow growth. Yeah. Yeah, I guess, yeah. Mm-hmm. Yeah, this I'm not sure. I know that at least for the symmetric product orbifolds, you can see, like, there's you can check easily from the polar states of the seed whether you get fast growth or slow growth. And in that case, but this is very special, yeah. And in that case, this will be like square root. So alpha will be 1/2. It's either 1/2 or 1 for symmetric orbifolds. Yeah. Okay, so these are the sparse weak Jacobi forms. And what we would like to understand now is how we extract the asymptotic behavior of the Fourier coefficient. So how do we extract the density of heavy states? And the way that we will do it is using crossing kernels. So the first step in this process is to replace the density of states here by some function, a function that depends on some, well, actually a distribution that depends on continuous variables, so that we replace the sums in the definition of the weak Jacobi form by these integrals. And yeah. You mean rho? It depends on delta and on L modulo 2t. Yeah. Yeah, if it depended only on delta, it would be much easier to do. And right, exactly. Yeah. Yeah. And so the way that we will extract the density of states is we will follow the usual approach. We apply a modular S transformation to this object. Then we do an inverse Laplace transform. And we can obtain the following crossing equation that relates the density of states to the density of states with this so-called crossing kernel. So the crossing kernel is defined in this way. The modular S transformation I mentioned before is here. The inverse Laplace transform is here. So we have this integral. This is divergent. We have to be careful about the choice of contour. And we can get the following expression. And one interesting thing about this expression is that the dependence on these charges L appears only in this phase, and then the rest depends on the index and the discriminant, okay? And something else that is worth noting about this expression is that here I is a Bessel function, and this Bessel function has an index minus 3/2. The important thing is the minus, as we will see soon. Okay, so we can approximate the crossing kernel for large values of the argument because ultimately we're interested in extracting the asymptotic density of states, the density of states for heavy states. And then you find that this exponential can have two types of behavior. So if delta prime is less than 0, so for the polar states, this is an exponential behavior, whereas for the non-polar states, this is oscillatory. And so we throw those oscillatory terms away. We only keep the exponential growth. And this ultimately means that we can approximate the crossing kernel as follows. So we write the crossing equation by distinguishing between the contribution of light and heavy states. This gives oscillatory behavior, so we drop it. And so our approximation for the crossing equation takes this form. So this is an expression that depends on this crossing kernel and just the density of light states. Okay? Sorry, say that again. Well, it's like corrections that are exponentially suppressed. So I'm going to ignore all exponentially suppressed corrections to this expression. They're exponentially suppressed compared to the answer coming from the light states. Mm. Yeah. Yes. Yeah, yeah. Exactly. Yeah. Yeah, yeah. So I will compare it now. Yeah. So a natural question to ask is how good is this approximation? And so for weak Jacobi forms, there's actually an exact formula for the density of heavy states. This is known as the Rademacher expansion. And we can write this formula as a crossing equation as well. So you have the density of states here, you have the density of light states on this side. So here you're only summing over polar states. So this is similar to what we had before. And you have here a restricted sum over the values of the charges because of this condition that this only depends on L modulo 2t. And then you can ask what is the Rademacher kernel given by, and here's the expression. So this Rademacher kernel consists of a sum of many Bessel functions, here weighted by this parameter c. There's this additional element here, which is a Clusterman sum, where the dependence on n and L prime enters. For us, the important thing is that we want an asymptotic density of states for holographic weak Jacobi forms, where this index here, t, is going to be large. So the only important thing for us is that these Clusterman sums go like 1 over square root t, okay? And so there are many differences between the Rademacher kernel and the crossing kernel. This is a sum of many terms. And one important difference as well is that the index of this Bessel function is 3/2 instead of being minus 3/2. So if you take both Bessel functions, the integrands are basically the same. The only difference comes from the contrary of integration. But it turns out that if you try to compare these two Bessel functions, that the difference is exponentially suppressed. So this is true for any two Bessel functions, not just minus 3/2 and 3/2. By minus nu and nu, there's an exponential suppression. The difference is exponentially suppressed. And so what we find is that the Rademacher and crossing kernels agree up to non-perturbative corrections. So we find an equation of this form. Okay? Right. Yeah. Yeah. So here I'm looking at the term c equals to 1. This one would be like the term c equals to 2. So the term c equals to 2 gives you the first correction here. So it turns out that the corrections coming from the different Bessel functions appear later on. The first correction comes from the c's. It's already exponentially suppressed. Okay, so yes, it could be subtle. Yes, indeed. Yeah. So in this sense, we say that the crossing kernel is going to be a good approximation for what we want to do. Yeah. Yes. Yeah. Indeed. So yeah. Mm-hmm, mm-hmm, mm-hmm. Indeed. Yeah. We didn't do this, but yeah.
pi minus 0 and 1 and then you can power them for the state so that the wave magnet of the right? So there's an Jacobi form of wave minus 2 of wave of index minus 2 and then we multiply for 6. You can extract something out of this that is not going back. And it's that it's
Okay, so I've told you about these weak Jacobi forms, the type of weak Jacobi forms we're interested in, and how we're going to extract asymptotics. So now I will just tell you the results of our analysis, and then I will apply it to the context of black holes. Okay, so the crossing kernel allows us to estimate the density of heavy states when the discriminant of the state is large. And the answer will depend on the density of light states and the relationship between the discriminant of the state whose density you're trying to estimate, and the density of the most polar state, and the discriminant of the most polar state. So basically, what we want to solve is, or want to do is do these integrals here. And what's interesting about this expression is that this term here that comes from an approximation of the crossing kernel, this is already like the Cardi type of growth that we expect. But then you have this density of light state, so there will be a competition between these two terms here. Okay? So now I will consider different regimes in which we can evaluate this expression via saddle point approximation, basically. So the first regime I'll consider is this zero case is the Cardi regime. So this is the usual regime where the discriminant of the heavy state is much larger than the discriminant of the lightest or most polar state. So in this regime, the crossing equation is dominated by the most polar state, or by the ground state, and so we find that the density asymptotic states is given by the expression given here. So there are two things to highlight here. First, we have this exponential growth, which basically comes directly from the crossing kernel. This is the Cardi growth. And then we have the logarithmic corrections that are determined by this expression here. Something important to keep in mind here is that the ground state for these weak Jacobi forms is not necessarily 1. So it's highlighted in red here because this is important for matching the logarithmic corrections. So then we will move to a more interesting regime, which is a holographic regime, this universal regime where the delta scales linearly with delta naught. So in this case, the crossing equation is again dominated by very light states, and in the saddle point approximation, we find this expression is the same expression that we had before. But this expression is valid in a different regime, and for this to be true, we need to make assumptions on the density of light states. So we need to assume that the density is either fast or slow. Okay. So what's interesting about this expression is that the log corrections are universal. So they do not depend on the distribution of light states. They only depend on the density of the ground state. And these, as we will see, can be determined just by symmetries. And we also see that sparse weak Jacobi forms can satisfy a weaker version of the HKS bound, which is true when this parameter gamma here is greater than 1. But the most interesting aspect of this analysis is that it turns out that there's an extended regime of validity of Cardi's formula. And this extended regime of validity of Cardi's formula is valid only for slow-growing forms. So, meaning that it's now possible to extend this regime from the case where delta is greater than delta naught to a case where delta is less than delta naught. So this takes us to the non-universal regime. So the universal regime was characterized by this expression here, and it's universal because the logarithmic corrections are universal. In the non-universal regime, delta is less than delta naught, and the corrections will also be non-universal. So in this case, the crossing equation is no longer dominated by the very light states, and so we have to be more explicit about how we parameterize the density of light states. So the way we will do it is as follows. So we will bound the density of light states by an expression of this form. Here, rho naught is just the density of ground states that I mentioned before. This function g has only polynomial growth on its arguments, and it will affect the logarithmic correction. So it will affect the actual number that we get out. And then in the exponential growth, we have this other function, f alpha, which will control the location of the saddle. It will determine the regime of validity of Cardy's formula, and it will also affect the logarithmic corrections. Okay, so now it turns out that to make progress on this, we need to make some further assumptions because these functions here depend on two arguments. So we will make two different assumptions, and we make these assumptions because they can be easily applied. Or we have an application to the black holes that I will consider in the last part of the talk. So the first assumption we will make is that these functions that appear here are democratic distributions. And by this we mean that if you take, for example, any scaling of the arguments by some large number, lambda here, that this function scales as follows. And the function g also scales in this way with this parameter omega here and a parameter alpha here. And alpha here is less than 1. So the example to keep in mind here is a growth that goes like exponential of square root of n, for example. In fact, we're going to assume that this parameter alpha here is 1/2 because this will be physically relevant later. And once you do the saddle point approximation, you find a density of states in this non-universal regime is given by an expression of this form. So here in blue, we have again Cardy's growth. So the leading behavior is still Cardy, but you have logarithmic corrections that now depend on the particular details of the light states. So these 3/2 here is determined by alpha here 1/2, and there's also this W here, which is determining how the density of light states grows polynomially for large values of n and l, or large values of the discriminant. Okay, so that's the first case, and we will have an application of this later on. But it turns out that there's another very interesting case that also has an application, and it's the case when we have a so-called autocratic distribution. So an autocratic distribution will be one that is sensitive only to the scaling of n, namely the energy. And in this case, the density of light states becomes effectively neutral. So we ignore the other parameter in these functions. So this expression that looked a bit complicated before, now is parameterized in this way. There's a density of ground states. There's a polynomial growth in the energy parameterized by this omega, and an exponential growth, n to the alpha, that appears here. Okay? And if we try to solve use the saddle point approximation to solve the Crossen equation, we cannot find an analytic solution in this case. We can only find perturbative solutions. We can only find perturbative solutions in these 3 different regimes, okay? So there are regimes where delta scales with respect to delta naught in a particular way that is determined by this alpha that appears in the exponential growth of the light states. Okay, so there are many cases. So there are these 3 cases that I will go through. So in this, yeah.
So
yeah.
if I look at this formula,
yeah.
I expect that this also that there's some like fields like
Yes.
so what
Well, this will be they will come from the master spectrum of supergravity, basically.
previous case just
Well, it's everything. You have to look at the full spectrum of the theory and then try to determine what this omega is. Yeah. We will see an explicit example a bit later.
that's what it is delta. You know, you have the delta down.
Oh yeah. Yeah. Yeah, so this is because there's a particular case we want to study. And in this particular case, this is true for the supergravity spectrum. Yeah. Yeah. Okay, so there are these different cases where we can solve this equation, and it's a bit technical, but I promise you it's very interesting. So in this regime, so delta much greater than delta naught to this power, we find the following density of heavy states. So there's a Cardy type growth, which is good. You could in principle apply this to understand black holes. There's logarithmic corrections, and these log corrections are sensitive to these parameters alpha and omega that characterize the density of light states. Okay, there's nothing too special about this case. This case is a bit more interesting because in this regime, the light states dominate over the Cardy growth. So if you remember, the crossing equation has the Cardy growth and the light states, and there's a competition between them. And in this case, it turns out that the light states win, so that the asymptotic density, the leading term, does not look like Cardy anymore. It looks like this type of growth. So we don't expect this case to be relevant for black holes. And in principle, you would be done with this analysis. But there's another interesting case when this delta scales exactly in this way. Yeah. Which one? Oh, this one here. Yeah. So this type of growth is if you just do thermodynamics, you could determine the type of growth. So I think if you just do thermodynamics, the type of growth should be like e to, I will throw some 2 pi's, and then it would be something like this to some alpha. But this alpha depends on the dimension. Yeah, so, but it's less than 1. Yeah, so some gas of light particles in a box, you can find it, yeah. Yeah, so we don't expect this case to be relevant for black holes, but something interesting happens in this case. And what happens in this case is that the density of light states and the Cardy growth are comparable. So what you find is an expression of this form. So the log corrections in this case are the limiting case of the 2 previous regimes. So this is compatible with what we did in the other regimes. But the interesting thing about this formula is the leading term. So the leading term looks like Cardy's formula, but now there's a number here, zeta. There's an order 1 correction, okay? So this would be like saying that the entropy of your black hole satisfies the area law over 4G times some number of order 1. It's not just area over 4G. So that's interesting. Of course, I haven't applied this to black holes yet, but this is a hint that this will appear very soon, okay? So even though this case is a bit strange because of this factor here not being exactly Cardy, it turns out that it will be relevant for black holes, okay? Okay, so this is the summary, and yeah, so this is the summary of the different regimes of the weak Jacobi form. So I have plotted this ratio here. There's a regime where the log corrections are universal. In this case, the growth of light states can be fast or slow. And the log corrections in this regime are non-universal, and the growth of light states must be slow in this case. And the leading exponential behavior in this regime here is Cardy, so we expect this to be gravitationally relevant. This was the case where it was not Cardy, it was just like this gas of particles, so we don't expect it to be relevant. And then there's this dotted line here, which is a case that would be marginally relevant, okay? And it will turn out to have an application in the next part of the talk. Okay, so now let me move to the logarithmic corrections to the entropy of black holes. So the log corrections to the entropy of BPS black holes in supergravity can be computed, in ungauged supergravity can be computed using the quantum entropy function, which is basically the Euclidean path integral in the near horizon ADS2 region of the black hole. So in this approach, it's important to take a uniform scaling of the black hole charges. So for example, for a 4D BPS black hole with charges Qi, you would take this scaling of the charges where lambda is much greater than 1. This uniform scaling guarantees that you still have like an ADS2 cross S2 near horizon geometry, and also make sure that massive fields do not contribute. So the answer will be only sensitive to the low energy, the massless spectrum of the theory. So in this case, the area of the black hole would scale with this parameter lambda squared, and the logarithmic correction to the entropy takes a form that is given here. So this log correction arises from a one-loop correction to the leading saddle in the path integral, and it's determined, as I said, entirely by the low energy effective action, which means that it's independent of the UV completion of the theory. Yeah. I think so. Which previous one? Yes. I see. Well, yeah. Right. Right. Okay. So this computation of the log corrections, it's independent of the UV completion. So for these reasons, this provides, in the words of Ashok Sen, an infrared window into the microstates. And this coefficient, A gravity, receives two types of contributions. There's a contribution that comes from local fields that you can compute, say, through the heat kernel method. And there's a contribution from zero modes. So this was mentioned before in Leo's talk, that in even D, both of these terms will contribute, meaning that log corrections are sensitive to the spectrum of supergravity. But in all dimensions, we instead find that this A local is zero. So the log corrections are in some sense universal. So they're determined only by the zero modes, which are related to symmetries. So in particular, in 4 and 5 dimensions, we have these two expressions. So in 4D, A local is given by this expression here. N is the amount of supersymmetries you have, and NV and NH is the number of vector and hypermultiplets in n equals 2 notation. And the number of zero modes is 1, and similarly in 5D, this is 0, and the number of zero modes depend on the number of vector multiplets that you have. Now, in many cases, this coefficient A gravity has been reproduced using microscopic counting formula from string theory. And in these cases, the near horizon ADS2 geometry can be uplifted to ADS3, where the log corrections are captured by some weak Jacobi form. So the idea that we have is the following. Say you start with some BPS black hole. In the near horizon region, you get an ADS2 geometry times something else. And in this case, you can use Ashok's quantum entropy function to extract the logarithmic corrections. But alternatively, you can start with this black hole and do a dimensional uplift to a higher dimensional black hole, whose near horizon region is ADS3. And then this theory of ADS3 here has a dual CFT2, and this dual CFT2, in this dual CFT2, you can compute something like the elliptic genus or a related quantity, which is given by a weak Jacobi form. So our goal is to extract the logarithmic corrections from this weak Jacobi form instead of from this quantum entropy function. And an important thing, or maybe the crucial thing about doing this sequence of steps, is the fact that in the quantum entropy function, you have to take this scaling of the charges. So this uniform scaling of the charges for the weak Jacobi form will translate into probing different regimes of the weak Jacobi form. So different relationships between delta and delta naught, which is the reason why we were so careful in the first part of the talk in finding the density of states in different regimes. Okay? And correspondingly, the logarithmic corrections from the weak Jacobi form perspective may be universal, so determined by symmetry, or they may be non-universal, meaning that they depend on the distribution of light states or the supergravity spectrum. Okay, so now let me try to apply this to 3 different black holes. The first one is half BPS black holes in 4-dimensional n equals 4 ungauged supergravity. So in this case, when n equals to 4, the number of vector and hypermultiplets satisfies this condition. And as a result, the log corrections to the entropy of black holes actually vanishes. So you have the leading area over 4G, and then the coefficient of the log corrections turns out to be 0. So we want to reproduce this 0. So this black hole is obtained from reduction of the D1, D5P solution of type 2B supergravity compactified on K3. So we can uplift the near horizon geometry as follows. So the near horizon geometry of the 4D black hole is ADS2 cross S2. It can be uplifted to ADS3 cross S3 cross K3, where here ADS3 cross S3 is the near horizon region of the 6D BPS black string considered by Strominger and Baffa. And so the spectrum of supergravity on this background is organized into chiral primary representations of the 4,4 algebra. And the elliptic genus provides a signed count of these states. And this elliptic genus corresponds to a weak Jacobi form, which is given by the elliptic genus of the symmetric product orbifold of K3. So this is the weak Jacobi form that we're interested in. It has weight 0, and the index, or the value of the discriminant of the most polar state, grows with the central charge. It grows with n. Okay, so here comes the crucial point. In the quantum entropy function, we need to take a uniform scaling of charges. What one does is one takes the charges of the black hole. You need to first translate them into the language of the weak Jacobi form, and then compare how the scaling of the charges translates to the scaling of the parameters of the weak Jacobi form. And so you find an expression like this. So for these black holes, what this means is that we're in the universal regime, a regime where delta scales linearly with delta naught. So in the universal regime, we just use the formula that we had before for the asymptotic density of states, which I have written here again. And the log corrections basically are determined by this rho naught. So I'm going to conveniently parameterize rho naught in the following way, such that the log corrections takes this form, okay? So I have just taken the logarithm of the previous formula and rewritten rho naught in this convenient way. Now, the question then becomes, how do you determine the C naught for this weak Jacobi form? And you can determine it in two related ways. The first way to see what the value of C naught is to just count the degeneracy of ground states in the elliptic genus of K3, not of the symmetric orbifold, but the elliptic genus of the seed. So here, the number is 2. And the reason for this is because to the elliptic genus, you only, to the ground state in the elliptic genus, you have states of this form. So vacuum on the left, chiral primary on the right. The vacuum of the theory is of this form, so it contributes a 1. And it turns out that the SU2, one of the SU2 currents is also a chiral primary. So it's also this form. So it gives you the other one. And so this number is 2. And if you plug 2 here, then the logarithmic correction vanishes. But it turns out that this result is way more universal. It does not depend on the details of K3. It only depends on the fact that you have n equals 4 supersymmetry. So it turns out that the degeneracy of Ramond ground states, the degeneracy of Ramond ground states should be given by this expression. And here J03 scales like delta naught. And this you can see by doing spectral flow from the NS sector to the Ramond sector. So it turns out that this coefficient Z0, being 2, is universally determined by symmetry. We didn't even need to know that we have the elliptic genus of the symmetric product orbifold of K3 to do this calculation. And so we find that the logarithmic corrections vanish in agreement with the ADS2 result, so we get a 0 here. Now, why is this analysis particularly interesting? And this is something that I don't understand, is that from the ADS3 perspective, the result is trivial, as I emphasize. This coefficient was universally determined by supersymmetry. It did not depend on any of the details of the theory, on the light states. Whereas from ADS2, the result appears to be non-trivial. because it comes from careful cancellations of terms in A local. So A local is sensitive to the spectrum of supergravity, and there's a careful cancellation of terms. Of course, that cancellation is still dictated by supersymmetry, but there are two sort of different perspectives on the same result from different dimensions. And we will see that this situation persists. So I will now consider another case where the situation is reversed. And these are BMPV black holes in 5 dimensions. So in odd dimensions, this contribution to the heat kernel vanishes. So there's only a contribution from 0 modes. There are this number of vector fields. So the entropy, the logarithmic corrections to the entropy are given by this -4 that appears here. Now we can do the same dimensional uplift that we did before. Now ADS2 cross S3, the near horizon of the 5D black hole, is uplifted to ADS3 cross S3 cross K3. The weak Jacobi form we're looking at is exactly the same elliptic genus. It's the same object that we had before, but crucially, the scaling of charges in the 5D black hole corresponds to a different scaling limit for the weak Jacobi form in ADS3. So the same weak Jacobi form is giving me the log corrections of 5 dimensions and 4 dimensions. And the reason why this is possible is because these log corrections are hidden in different regimes of the weak Jacobi form. So the scaling of charges in 5 dimensions implies the following relationship between delta and delta naught. And this belongs to the non-universal regime. In fact, it belongs to this democratic distribution in the non-universal regime. In this case, we do need the details of the elliptic genus. So the details are here. So this is how the light states grow. They're bounded by a function of this form. And these coefficients here, alpha, I mentioned before, is 1/2. Omega, you can determine, is given by the number of ground states in the elliptic genus of K3 and the number of the first excited state. So this is something that you can compute. So if you plug this into the formula we had before for the democratic distribution in the non-universal regime, you get an expression of this form. And these log corrections match exactly the ADS2 result. So you get the -4 that you expected from the lower dimensional calculation. Now, what's interesting about this result is that from ADS3, the result is not trivial. It depends on the distribution of light states. To get this -4, you need to find exactly what this omega, which determines the polynomial growth of the light states, is. You need to know in what regime you are. So it's a regime where alpha is equal to 1, and then you can get the correct result. But from the point of view of ADS2, the answer is sort of trivial because the local contribution to the kernel vanishes. So there's only a contribution from 0 modes, which is -4. So it's sort of the opposite of what happened in the previous case. So this is something that I don't understand, that I would like to understand better. Okay, so these are the two cases with n equals 4 supersymmetry. And now I will go to a more interesting and challenging case with n equals 2 supersymmetry. So these are half BPS black holes in 4-dimensional n equals 2 ungauged supergravity. So in this case, the logarithmic corrections depend on data from a Calabi-Yau threefold. So there's a number of vector fields, a number of vector multiplets, and a number of hypermultiplets. So this is the expression that you would like to match using the appropriate weak Jacobi form. So this black hole in 4 dimensions can be obtained from reduction of M2 and 5 solution of M theory compactified on a Calabi-Yau threefold times a circle. In this case, we can uplift the ADS2 cross S2 near horizon geometry to ADS3 cross S2 times the Calabi-Yau threefold. And this is the near horizon region of the 5D BPS black string considered in this paper. So the relevant weak Jacobi form for the theory in this background is a so-called modified elliptic genus of the MSW CFT. So this is a CFT with n equals 4 supersymmetry only on the right movers. So this modified elliptic genus takes this form, and it's a very complicated object for a number of reasons. It turns out that the algebra of the MSW CFT is not the small n equals 4. It's not the large n equals 4 either. It's a contraction of n equals 4. But because of the large n equals 4. But because of this fact, if you don't put the f squared here, the elliptic genus would vanish. So you need to put this f squared here. And there's a number of subtleties with this object. There's a continuous part of the spectrum that you need to remove. So that's what I put this tilde here. There are more potentials, so there are more charges than the case we considered before. For the elliptic genus, or for the weak Jacobi forms I considered before, there was just one charge. Here now you have a number of NV charges and NV potentials. And perhaps the most, or something that is very different from what I mentioned before, is that this object is no longer holomorphic. It depends both on tau and tau bar. However, it turns out that this tau bar dependence is trivial. It's determined by some heat equation. There's some differential equation to determine the dependence of this object on tau bar that is determined entirely by the potentials. So something that you can do is you can set tau equals to tau bar and get the following expression, which is now again holomorphic. From this expression, you can reconstruct this one, this tau bar dependence easily. It's sort of a trivial dependence on tau bar. Now, with all of these subtleties out of the way, this is the object that we would like to understand. And this is a weak Jacobi form that no longer has weight 0. It has weight -1. And the index scales like the central charge to the power 1/3. Okay? And these are properties that are determined basically by this MSW CFT. Okay, so now we can play the same game as before. You do the scaling of charges in the 4-dimensional black hole and try to translate this into the quantities that appear in this modified elliptic genus. And it turns out that you find the following relationship. And this, again, puts us in the non-universal regime. So the log corrections of this black hole are going to be captured by the non-universal regime of this weak Jacobi form that I mentioned before. And okay, so I don't have a lot of time, but this actually I think is very interesting, and it's very subtle how to determine now the density of light states. So in the previous case, we had a very concrete answer. We had the elliptic genus of the symmetric product orbifold of K3, and a lot is known about this and how to extract the density of light states. Here the situation is more complicated. So the asymptotic density of light states can be determined from the spectrum of supergravity on this background, and different authors have tried to compute this expression before. So the contribution from supergravity takes this form. There's no charges in this expression. All the states are uncharged, which is the reason why we needed to discuss this autocratic regime, because the density of light states does not depend on the charges, only depends on the energy. There's this McMahon function here that depends on the Calabi-Yau data in this way. So this is how these terms will appear eventually in the logarithmic corrections. And there is a small subtlety. There is this eta function to the power of s. These will change your logarithmic corrections. And different authors have computed this value of s and obtained different values. Okay? So we believe the correct value of s is actually 0. One of the reasons is that this is required by the OSV formula, which relates the partition function for the microstates of the black hole to some partition function of a topological string. And also for the matching of the central charge of this MSW CFT. So in this interesting paper, they showed that if this S is non-zero, then you cannot match the central charge to be to the correct value here. So this makes us believe that S is actually equal 0, even though this has not been calculated explicitly. And I think the reason it has not been calculated explicitly has to do with the subtleties of this being a contraction of the large n equals 4 algebra. Okay, so once we know what this expression is, which basically means you ignore these two terms, it's just given by this McMahon function, then you can estimate what the density of light states is. So you can see that the density of light states when n is large grows in this way. this is the polynomial growth is sensitive to the Euler characteristic, and then you have this value of gamma, and you have this value of alpha, which is equals to 2/3. And the important thing about this value of alpha, so this growth here is n to the 2/3. What's important about this growth is that this relation is satisfied. Okay? So this means that we are in a regime where the asymptotic growth of the weak Jacobi form is not captured by the Cardy formula. Okay, so the expression is a bit more complicated than what I showed before because you have multiple charges, you have weight, but we can ignore this and we can go to the final expression. So the final expression that we obtain is given here. So the logarithmic corrections match exactly what Ashok and friends computed before, but the leading term, the area term, does not match. So this is a case where our understanding is that the quantum effects have taken over and overcome the classical action. So the leading term is not just area over 4G. The leading term that we get is corrected by this zeta here. I don't think so. Well, I'm not sure. So this thing depends on this gamma, but also will depend on the ratio of delta to delta naught. So if you try to extract this formula for some, so this ratio of delta naught, delta has to scale like delta naught to this power, but that ratio could be any number. So you could make this number here anything you want. But it's a small number. It's not a number that grows. It's not a large number. It doesn't grow with delta. Okay, so I think this is something very interesting, and I don't know if this is a hint for why this is happening, but this growth of n to the 2/3 that appears here is the same growth that you expect for a higher spin theory in 3 dimensions. So maybe this fact is related to that, but that I'm not sure. And the fact that the matching is sensitive to the weight, so this matching is sensitive to the weight of the weak Jacobi form, the ground state degeneracy, and a proper accounting of the light spectrum. So I take this as further evidence that this S here for the density of light states should indeed require S to be 0. Okay? Okay, so I am 2 minutes and 32 seconds over time. So let me just end with a summary of what we have done. So we had this picture before about the logarithmic corrections, whether they're universal or non-universal. And these are determined by whether we have fast or slow growth. And we have also seen that in different regimes and in different cases, you can have a Cardy growth or a non-Cardy growth. And now we can also find different examples of different black holes that fall into these regimes. So we have the 4D n equals 4 black holes in the universal regime, the 5-dimensional ones in the non-universal regime, and then equals 2 5-dimensional black holes in this very interesting region where the leading growth is Cardy with this modification of order 1. Okay, so let me end here. Thank you.
Thank you very much for the very interesting talk. So are there any questions?
Why can you do the uplift? It's the near horizon geometry ADS2. Why can you uplift to ADS3?
Yeah, because this black hole, the black hole itself, I can obtain from a higher dimensional black hole. So this is already true, and I just I take the near horizon in this. I'm not going directly from here to here, but I already have the uplift of the black hole itself. So then I just take near horizon limits in.
Are you changing the system? I mean, you want to study, for example, the ADS2 black hole. Somehow you change the problem to another system.
No, I want to study this black hole, but the log corrections are computed by going to the ADS2 near horizon region.
Right.
So here I'm still studying this black hole from a higher dimensional perspective from its near horizon region as well.
Yeah, that's where I don't understand. Why can't you do this?
Yeah, maybe I can follow up because I
Sure.
think I compress in the same direction. So this is you can think about these things as you have a solution, you can put your solution wherever you want, as long as it's a solution. But this is only like consistent truncation. This is about the solution, not about the theory. So by putting your solution in different theories, you're forgetting some information about the offshore part that might be important for this computation.
Yeah.
I think that's the question. And I also wanted to hear what you think about that.
But here only it's only like the light spectrum. It's only the massless states that contribute in both cases, basically, right? So I think that's related to why we can do it. Sorry? Well, the answer is sensitive to the massless spectrum. That's all I can say. Yeah.
Are there more questions?
But so these were only for the lower dimensional theory. So these were only computed. These were already computed before for the near horizon region of the lower dimensional black hole. So ADS2 cross S to some power. We didn't. No, we didn't check. Yeah. But I've seen papers that have done this. There's a paper by okay, I forgot the by Finn Larsen that computes the heat kernels in 5 dimensions, then does dimensional reduction and computes them in 2 dimensions. Or sorry, in 1 dimension lower. And the computation in 1 dimension lower is way more complicated because you have to take care of the Kaluza-Klein power. But he can show that these match. You can just do the computation.
So any more questions? So if there are no more questions for Luis, let's thank him again.